Okay, welcome everyone to this continuation of what is quantum topology. We are already at part number 10. Yeah. And on part number 10, I would like to ramble a little bit about what mathematics is all about. Yeah. What is mathematics all about? Mathematics is all about the science of equality. Maybe not, who knows really. But a lot of people think this is mathematics, right? 2 plus 2 equals 4. Yeah? The science of equality. Yeah, in some sense it's true, and in some sense that's not really true. Right? So for example, real world might say pi is 3, and mathematics might say pi is that expression. Double check me on that, whether this is actually true or whether I have a typo somewhere. But I think this is roughly how it should go, right? Math would think this is how it goes. But in some other sense, mathematics is a science of redefining equality. Yeah. So literally, people would say 3 is approximately pi. 3 is approximately pi. Still true. 3 is approximately pi. What I wanted to say is pi is approximately 3, or this 3.1. You know, the people that just list God knows how many digits of pi. So in some sense, mathematics is a science of equality. In some sense, mathematics is a science of redefining what equality means. And in category theory, you usually just redefine what equality actually means. Yeah? So let's have a look at the science of equivalence. Maybe that's what it's supposed to be. So here we have two groups, Z mod 2, so addition, 0, 1 in addition. So 1 plus 1 is 0. And I could represent it as a fruit group, apple and orange. So apple plus apple is apple. Apple plus orange is orange, as everyone knows. And orange plus orange is apple. Yeah. So they are clearly the same group if you just think about it. There's an obvious mapping 0 to apple, and I guess 1 to orange. Yeah. But they are strictly speaking not the same. One of them is Z mod 2, and one of them is a fruit group, right? The sets are different. So strictly speaking, this is not part of our science of equality, but it's part of our science of equivalence, right? They're equivalent or isomorphic or whatever people call it. The same up to renaming. They're really the same objects if we think about them as groups. The fruit group and Z mod 2 are exactly the same, right? And the map is just sending, as I said, 0 to apple and 1 to orange. Yeah? So science of equivalence instead of science of equality. This is something you learn way later in life. So this is like what most people think mathematics is. This is what mathematics actually really is in some sense, but you learn that much later in life. And category theory takes that extremely serious. There's essentially no equality in category theory. Yeah? Category theory goes one step further. For example, our category of finite sets. Yeah, the objects are finite sets. The maps are maps. Our category of the skeleton of that thing. Yeah, F set SK. The objects are just numbers, natural numbers, 0, 1, 2, 3, whatever, and the maps are bijection or whatever. These kind of type of maps like that between them. Yeah, just some maps from M to N in this case. Yeah. And M is just my shorthand notation for the set 0 up to M minus 1. And N is just my shorthand notation for the set 0 up to N minus 1. Right? So these are just the things. And there's an obvious functor between them, which just sends a set to its size and the corresponding map to the corresponding map on those funny sets, those pre-chosen sets that just represent the numbers M and N. And in some sense, again, these things are the same, yeah? Somehow, but in some sense, they are not the same. The right-hand side, the left-hand side, has way more objects, right? There are many, many different sets. And the right-hand side has just one set per equivalence class. Huh? So the left-hand side has way more sets. But category theory says, I don't care. It's exactly the same as in this case, on the left-hand side and the right-hand side. Strictly speaking, they are not the same, but of course they are the same in some other way. And category theory does exactly that. So we do not care whether one of them has more objects than the other. we care about the morphisms, we care about the arrows. We're doing category theory. We care about the arrows only, right? And that's why you define two different notions of equivalence of categories. One of them is being the one you always use, the equivalence, and the other one is a bit stronger. So, an isomorphism from C to D is a functor with an inverse. Yeah, fine. And those categories are called isomorphic if there's some isomorphism. Huh? There's some invertible functor. That's what you usually do it. Right? Something is isomorphic if you have an invertible, if you have an inverse. Yeah. And isomorphisms are bijections. Yeah? So objects and arrows, on objects and arrows. So the focus is really on objects here, because we want to have bijections on both. While equivalences only want to have bijections on arrows. So an equivalence is, there's a functor between them such that they're not the identity, it's kind of pseudo-invertible if you want. I haven't told you what up to natural iso is, but there's a natural isomorphism between them. So an isomorphism, a natural transformation, which is an isomorphism. And in this case, we call them equivalent. And equivalent is kind of the correct notion in categories. Yeah? So it's way weaker. You only have bijections on arrows. Yeah? And you don't have bijections on isomorphisms. On objects, as it should be. So really the focus as not on the objects anymore, as it should be in category theory, right? So here's an even more extreme example. So if you want to take the category of finite sets where the morphisms are just isomorphisms, yeah, then you can just draw these pictures here. Yeah, so an equivalent model of that would be a category where the objects are just boundary points, and I hope these pictures are not too unfamiliar at this point. So just boundary points, so let's just say natural numbers, here in this case 5, and here in this case 5. And an isomorphism is just some string connecting them. Yeah? So all possible string diagrams. So in this case, you can also formulate it differently. Category of finite sets and isomorphisms is equivalent, but not isomorphic, to the category where the objects are just natural numbers and the morphisms are just symmetric groups. Yeah? Then this is, again, the focus is on the morphisms, because bijections are essentially permutations of elements, just phrased in different language. Anyway, I hope you enjoyed this video, and I also hope to see you next time.